This video is about solving right triangles using trigonometric ratios. And before we get to some examples, I'd like to discuss some of the basic facts and principles we'll be using along this. So these are just some general notes we can follow. First of all, some facts. Things we know already that we'll have to use. First of all, we're going to rely on our acronym known as SOHCAHTOA. And of course, this helps us organize and remember all of our trig ratios. Remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We'll definitely be using those ratios as this video says. We're solving triangles with trig ratios. Beyond that, there are some general rounding principles we're going to follow, as we'll be needing to round for several of our answers. And those principles are these. I'm going to list a few of them here. First of all, side lengths, we are going to round to the hundredths place. Secondly, angles, if we get an angle answer for a triangle, we're going to round those to the tenths place. And thirdly, we're going to say don't round until the end. So if we round too soon, we'll be using rounded numbers in our calculations, but then that's going to create all kinds of error we don't want. So as a general principle, we're going to try not to round to the very end. Now we have to make sure we're speaking the same language when we label things. So we're going to follow a couple conventions on how to label our triangles. I'll draw a right triangle here as an example. Of course, the right angle is always labeled with a little box in the corner. And then the way that we're going to follow the conventions for labeling are as follows. Angles inside the triangle that are not the right angle, that leaves two of them, will be labeled with Greek letters A and B. And that's actually alpha and beta. Okay, so that's like A and B in Greek. Those are used for the interior angles that are not the right angle of a triangle. The side lengths of a triangle are labeled accordingly. So across from alpha, the side length that it's not touching, so that'd be straight across from it, that side will be called A, just the English lowercase a. Similarly, across from the angle beta, the side that it's not touching will be labeled B. And then across from the right angle, which of course is the hypotenuse, that's typically labeled as C. Sticking to these labeling conventions will help us communicate math very clearly. Now there are some definitions that we also need to understand for some of the application problems we'll eventually get to near the end of this section. And those are as follows. There's something called an angle of depression. And then there also is something called an angle of elevation. And we want to be able to know which angles those are talking about. So to illustrate this, I'm going to draw a little picture down here. Suppose we have ground. I'll just draw one line for the ground. And then I'm going to draw a couple dots that are one being kind of floating above the ground and one being actually on the ground, as you can see here. So on the top right, we have a dot floating above the line, and then somewhere on the left side of this line, there's a dot on the line. Now, I'm going to draw a couple other segments to help illustrate this. First of all, a segment connecting the dots, and then another segment parallel to the line we've already drawn that intersects the dot that's floating above it. So it's a line that's just kind of parallel to the one on the bottom, so that what you now look at is almost like the letter Z. A couple parallel lines with dots on them, and those dots are connected by a third line. So there are various story problems you'll see where maybe somebody's standing on a cliff up at the top dot, or somebody's standing in a field at the bottom dot, and the perspective of where that person is matters with the language here. So let's take, for example, first of all, somebody elevated up here at this dot that's floating above the bottom line. If that person is described as having an angle of depression, the angle of depression would be between the horizontal line of sight and the line segment that's angled down. So this angle right here is called the angle of depression. And then if somebody is standing down here at this other dot looking up at something, the angle at which their gaze looks up is called the angle of elevation. So that's the angle of elevation down there. And those are also listed in our book. We have to know when a certain scenario describes the angle of depression or elevation, which angle it's talking about. Basically, it helps if you know where the ground is and where some kind of elevated position would be, like up here, like in a hot air balloon or something, as you'll see these sort of problems say. So those vocabularies will help us get our pictures organized correctly so that we can attack and solve an application problem. Let's take an example of how we can solve a right triangle. And this one says to solve a right triangle for b equals 6 and alpha equals 56 degrees. Now, that's the only information given, and so with only that, we're going to solve this triangle, which means to solve a triangle means to find all side and angle measures of it. Now, we currently see no triangle, so that's our job to draw one, and the only thing matters is that it meets the description given. So we know it's a right triangle, and it actually doesn't matter which way you draw that, so I'm just going to draw a random right triangle. So it has to have a right angle to be a right triangle. Otherwise, it could be oriented frontwards, backwards, upside down. It doesn't really matter. And what we're told is that side B is 6. Now, what's side B? Well, it doesn't really matter. Remember, our naming convention is that typically across from the right angle, which is the hypotenuse, we usually call that C. Otherwise, A and B are just the other two legs. It does not matter which one's which. So I'll just, for fun, call this bottom side B, and they're telling us that that's equal to 6. Now, with that given information, we know that the other side not yet labeled we'll call A. Furthermore, given the convention of labeling, across from side A, where this angle is, that will be angle alpha, which they've told us is 56 degrees. With only these two pieces of information given and a picture drawn, as you can see now, we have to find all the other angles and sides that we don't know yet. So in other words, I want to know what C is in length, I want to know what A is, I want to know what angle beta is, which is of course way up here across from side B. And of course the right angle across from side C is 90 degrees, that's not going to change. So in order to find any of this information, we're going to have to rely on our trigonometric ratio and just some basic facts about triangles. For example, one fact we're going to pull in here to be able to use is this. All the angles of a triangle must add to 180 degrees. Now that's something that can be proven in geometry. It's beyond the scope of where we need to go now, but we're just going to use it as fact. And so if that's true, notice we have a right angle, which of course is 90 degrees. We already know that this given angle is 56. That means that if I add those together, so 90 plus 56, okay, that's two of our angles. If I add the third angle, which is beta, those must all add to 180 degrees. Well, this is a simple equation to solve for beta, so let's go ahead and do that. We'll add 90 and 56 to get 146. So 146 plus beta equals 180. We'll then subtract 146 from both sides. This is just basic algebra, and we're getting, so beta will be 34 degrees. All right, we'll go over to our triangle where beta sits and label it as 34 degrees, just so we know we have that all set. So now, as you can tell, all three angles are known. 90 degrees, 56 degrees, and 34 degrees. Our remaining task will be to find any missing sides. This is where we're going to have to utilize or rely on our trig ratios. And we're going to have to know one side at least, which we do. B is 6. And then we're going to pick on either A or C to find next. It does not matter which one. And we're going to have to use one of our angles to find it. So I'm just going to pick on some things here. There are many choices you could make. But let's say, for example, you wanted to find what A was, side A, and you want to use, let's say, the given angle of 56 degrees, which was alpha over here. If I want to find side A and utilize angle alpha, which is 56 degrees, Now we're going to just label our triangle according to its three sides that we know, right? So it all matters on which angle you pick. If I've picked 56, I'm going to star that angle so I don't forget. That's where I'm orienting everything else from. Now the labels go as follows. The hypotenuse, of course, is always just the hypotenuse. That doesn't change. So I'm going to label that hype for hypotenuse. And then if my angle of choice is 56 down in this bottom right corner, that means all the way across from it, where side A is, will be the opposite side. So I'm going to label that opposite. Which leaves, of course, the side here at the bottom, where B is 6, as the adjacent side. So I'm going to label that adjacent. Well, all the trig ratios we know will soon be utilizing these three side lengths. The labels of these side lengths, of course being opposite, hypotenuse, or adjacent, will depend on which angle you pick. So I've already picked down here to use angle alpha, which is 56. If you had picked to use angle beta, which you could do, that would change not the hypotenuse, but that would change which sides are labeled as opposite and adjacent. Alright, so you just got to commit to the angle you've picked and label the sides accordingly. What I want to do, since I've picked to find side A, is use a trig ratio that's going to use its label, which is opposite, and then also the label of the side I know, which is down here, adjacent. Okay, so think, which trig ratio uses opposite and adjacent? That would be TOA, or tangent. So we're going to say the tangent of our angle of choice, which was 56 degrees, is equal to the opposite, which is A, over the adjacent, which is 6. This equation will allow us to find A simply by multiplying by 6 on both sides. So these 6's will cancel on the right side. And we're left with A equals 6 times the tangent of 56 degrees. And this is now a value that our calculator will handle for us. Let's pull out a TI-84 calculator and make sure that, first of all, we turn it on and make sure it's in degree mode, since that's what we're using. So if we press the mode button and then make sure that the third option down, it says either radian or degree, make sure you go over to degree and hit enter so that degree mode is selected. Then we'll hit second quit. And now we just want to type in our expression, which is 6 tangent, or tan, and then 56. It will assume that those are degrees since we selected degree mode. We'll hit enter. So 8.8953658811. This is now the calculation for side length A. So we'll round this to 8.90. And yes, 90 means we're rounding to the nearest hundredth. And that's side length A. Alright, the only thing left is to find the side length for C. And since we know A and B already, we can simply utilize the Pythagorean theorem to find the other side, right? That's always true for right triangles. We can say that 8.9 squared plus B, which we know is 6 squared, will equal C squared. This means 79.21 plus 36 equals C squared. Now if we solve for C by taking the square root of both sides, of course plus or minus usually occurs with square roots here, but we're ignoring the negative because this is a side length. C is the square root of 115.21, which if we round that value to the nearest hundredth, as our convention says, this will turn into 10.73. Alright, so we know side length C, we were already given side length B, and we had found side length A earlier, which means we have now solved this right triangle. We know all side lengths and all angles. Let's look at another example where we want to solve a right triangle, but this time the given information is that side C is 15 and side A is 9.12. Pictures are very helpful here, so let's get a nice right triangle drawn and label the right angle with a box. Across from the right angle, of course, is always side C, the hypotenuse. So we'll label that over here, and they told us that that's 15. And then A could be either of the other sides, it doesn't matter which. I'll call this one over here A, and we know that is 9.12 as given, which means the side at the bottom, which we don't know yet, is side B. And notice no angles are given. Let's label the angles, though, according to our convention. Across from side B, up in this top corner, we'll have angle beta, and across from side A, in this bottom right corner, we'll have angle alpha. If we want to solve this triangle, that means we want to find all sides and all angles. Now, we already know two sides, and as we've mentioned, if you know two sides of a right triangle, you can pretty easily find the third side thanks to the Pythagorean theorem. If we set that up, we'll know that b squared, as we have it labeled here, plus 9.12 squared, that's side A, would be equal to c squared, which is given as 15, so 15 squared. Let's take it another step here, so we'll say b squared plus, now 9.12 squared, you can try that on a calculator. Remember, we do not want to round anything until the very end here. So if you square 9.12 on a calculator, it should give you 83.1744. You may be very tempted to round that to 83.2 or so. Do not do it yet. We're going to round at the very end and leave some ugly numbers in play here for now. So that's, of course, equal to 15 squared, which is 225. And we can get b squared alone here, which will leave us with b squared equals 141.8256. And then to get b, we'll just take the square root of those sides. So b is the square root of this number, 141.8256. So punch that all in the calculator and do not round anything until the very end here. So side length b, rounded to the hundredth place, should end up being 11.91. Okay, so now we know b. We already knew a and c, which means our sides are all set. Now this leaves us having to know one more of our angles, either alpha or beta, and once we get one of them, we'll be certain to get the other because all three of these angles have to add to 180, and of course our right angle is already 90 degrees. It does not matter which angle you pick. I'll just kind of pick on alpha here in this bottom right corner. We have to use now a trig ratio that will involve alpha and other sides that we know. Now, just as a strategy, I'd prefer to use a side that is not rounded if I can. Remember, the side we found, which was b, as 11.91, that's a number that we had to eventually round. So I'd like to try to avoid using it if I can, because using a rounded number creates all kinds of other errors, and then our answers won't be totally correct. So if we can avoid using b, that'd be nice. I'm trying to find alpha, so let's label the sides accordingly. If this is alpha, my angle of interest, across from it, I'm going to call this side opposite. Of course, hypotenuse is always the hypotenuse, that's c. And then side b is going to be our adjacent, which I'm actually trying to avoid now. So is there a trig ratio that will utilize an opposite and a hypotenuse? Of course it is. That would be a sine. Sine is opposite over hypotenuse. So I'm going to say that the sine of our angle, which is alpha, we don't know what that is yet, equals the opposite, which is 9.12, over the hypotenuse, which is 15. We can crunch that number on a calculator and end up with sine of alpha being equal to 0.608. That's just 9.12 divided by 15. Remember, we don't want to round anything here yet, and that's not rounded. Now, I want to find alpha, not really the sine of alpha. And so we're going to have to use an inverse trig function to get rid of this sine. You see, you can't just divide by sine. Sine doesn't mean anything by itself. You have to use an inverse trig function of both sides. If I apply the inverse function to both sides, I'll end up with just an alpha on the left side. And if I take the sine inverse of the right side, I'll have the sine inverse of 0.608. And as long as we're in degree mode, which is where we want to be here, we can calculate this with the calculator. So on our graphing calculator, we can find the inverse sine by hitting the second button and then the sine button. And we want the number 608 as our input, close off the parentheses, hit enter, and it turns out that we get 37.445 and so on. Now remember, angles we want to round to the nearest tenth, and so I'm going to set this value of alpha to be 37.4 degrees. All right, well, that's great. So we have alpha, and we got it using a trig ratio and an inverse trig function. But how do I find the only thing missing, which would be beta? You see, you could have chosen to work with beta instead of alpha, and maybe you would have that and not alpha. But we chose to find alpha first. The remaining fact that will get us beta is to recall that all three of these angles have to add to, that's right, 180 degrees. So if all three of these angles must add to 180, and I already have 90 taken care of, and now I have 37.4, if I subtract those two both from 180 degrees, I should get that beta is 52.6 degrees. Let's now take a look at an application problem, and it reads as follows. A television camera in a blimp is focused on a football field with an angle of depression of 20.3 degrees. If the field is 450 meters away from a point on the ground directly below the blimp, find to the nearest tenth of a meter the altitude of the blimp. Okay, well, without a picture, we won't be able to do too much with this. So let's get a nice picture going for this. Of course, we'll draw the ground. It's not necessary to draw a beautiful looking blimp. I'm just going to draw a dot in the sky to represent where the camera would be on the blimp. So what it said was that directly below the blimp we have a point on the ground, and that point happens to be, as it says, 450 meters away from the field. So somewhere way down the line we'll just put another dot over here. 450 meters away from it is the field. I'll just label this field. Alright, so we have the blimp way up here, and of course the camera from the blimp is pointed directly at the field, so we'll draw a line of sight to connect those. Now of course this is making a perfect right triangle. I'm going to label the right angle in the bottom left corner as I have this drawn, where the point directly below the blimp is on the ground. What we know is that the angle of depression for this blimp looking at the field is 20.3 degrees. So, as previously defined, if you imagine a perfectly horizontal line of sight from the blimp, it would be parallel to the ground, but the angle of depression is the one that would bend down away from that horizontal line of sight toward the actual line of sight. So that angle they're telling us is 20.3 degrees. Now, if that's true, and these angles together here would have to make up a full right angle, then if I take 20.3 degrees away from 90, we'll get a measure of 69.7 degrees for this interior angle of the triangle right here. So remember, these two angles, they have to add up to 90 degrees because they make up this right angle. So I'm just using that fact and saying, all right, 90 minus the 20.3 we already have equals what? Well, 69.7. Once we have an angle labeled inside our triangle, it's just a matter of picking the correct trig ratio based on what we want to find. The question to this was to find the altitude of the blimp, and they say to the nearest tenth of a meter. Okay, fine. Altitude means height of the blimp. Well, that would be the distance from the ground all the way up to it, which I'll label as this vertical side of our triangle, x. If my angle that's labeled is 69.7 in this top left corner, then that x side would be the adjacent side of the triangle, and 450 would be the opposite side. Of course, the hypotenuse is the sight of the line of sight from the camera down to the field, but we don't actually know that side length at all, and we don't actually need it. You see, all we need to do is find a trig ratio that's going to utilize the opposite, which we know as 450, and the adjacent, which we want to know as x. So opposite and adjacent, of course, hopefully it's sounding like tangent to you. We'll say the tangent of our angle, which is 69.7 degrees, is opposite, which is 450, over adjacent, which is x. All we have to do now is solve this equation for x, which we could do by multiplying both sides by x. So I'll multiply tangent of 69.7 by x and 450 over x by x. Of course, these x's on the right side will cancel, that's the whole point there, giving us x times the tangent of 69.7 is equal to 450, but then we really want x alone, so I'm going to divide both sides by the tangent of 69.7 degrees. Okay, so these tangents of 69.7s will cancel on the left side, which leaves us, I'll go down here at the bottom now to say x must equal whatever 450 divided by the tangent of 69.7 degrees is. Let's take out a graphing calculator and punch in this exact value. So 450 divided by the tangent of 69.7. Remember to make sure you're in degree mode. If you hit enter and get this answer, you probably are. If not, you probably aren't. So double check that. So if we round to the nearest hundredth, as our little convention says, we're going to say it's 166.46 for the length of x. Now, since that's a side length, I'm going to write it over here where it belongs, 166.46. We should also include a unit with this, and of course everything else is given in meters, so we'll say 166.46 meters would end up being the altitude or height of this blimp.